an activity that takes place only in laboratories. And I'm not a scientist myself, but I think that if you talk to scientists, you'll find that most of them think that while laboratories are useful, in a way the whole world is a laboratory for science. The presenter tonight is somebody who sometimes finds herself doing research in a Virginia Institute of Marine Science research vessel offshore from Virginia Beach. So that while you and I, some of us might actually be on the beach enjoying an environment of waves, wind, sand, she's out there in a boat studying it. That's only part of what she does, and she's here now to help you to see for yourself more about it. Dr. Kimball?
You take it for granted. You take it for granted. That sounds awful. Okay. However, if you're some of the folks who live along the beach and who have houses that have seen the extreme effects of storms, suddenly you don't take your supply of sand quite as much for granted. Can you start with that?
Over here.
Technology is doing me in tonight.
She's got it. The top button. The top button. There you go.
Okay. Sometimes we see a lot of sand. This particular area is down in North Carolina. And this is following a storm. This is sand that's actually covered the road to a depth of 6 feet. Part of cross-shore transport. A lot of sand. Like I said, a lot of sand moving. If I can get some help up here. Okay, you guys done before, about this much sand in everybody's hand. Start up this side, you guys start up that side. We're going to look a little bit. We're going to need lots of help. And you're going to see, if you look at your sand and your neighbor's sand and their neighbor's sand, that it's not all the same. There's a lot of diversity. Now, one of the things that's really important to know is terminology. Sand is a term that refers to grain size. And that's why I'm telling you that everything I'm handing out to you tonight is sand. It varies between 2 millimeters and 0.0625 millimeters in size. But the term sand doesn't have anything to do with what it's made of, what the composition is. That's an entirely different issue. And that's what's really important along both those factors, the size and the composition, that are really important when you look at how a beach behaves. Let me pass up a little bit more here. Get you guys started in the back. Take a little bit, pass it on. Okay. Now, what does the sand was? Sand is not made of sand. It is sand because of its size quality. What it's made of, mostly, is this stuff. That's rock, that's right. Does anybody know what kind of rock? Very good. Who said that? Quartz, here. Present. Quartz number. The rock and the rock art. That's what it's made of, mostly. Now, second, what is the other thing that most of our sand is made of? It's made of this stuff. Also white, but no, it's not granite. This stuff, yeah. Close, but not quite. Put that back down in front. That's right, it is a silicate. Who said that? Feldspar. Have a piece of feldspar. That is indeed what it is. Feldspar and quartz are the two most common continental rocks in this part of the country. Consequently, they're the most common constituents in any of our beach sands. Our beach sands come from the Piedmont, Blue Line, or Blue River. They do not come from the offshore sands. Now, if you all rub the sand a little bit in your hands, you'll see that there's some very dark fragments in there as well. Those are heavy minerals. They're called heavy minerals because they're denser than quartz or feldspar. Consequently, they travel along in the same packet of sand as a large quartz or feldspar particle, but they're much, much smaller. They have much different characteristics. Now, one of the most abundant ones in there is this stuff. Who said that? Who's my mica person? Actually, this is biotite. It's a type of mica, but it has a lot of iron in it. Something that is very much present in our sediments. The other thing that you'll see a whole lot of is this stuff. Recognize this? No. It's red. Dark red. No, it's not. It's a glassy, very glassy garnet. Are you a geologist by chance? That's wonderful. You're going to have quite a collection here. That's a garnet. Yeah. The other thing that's in here that you'll see in various percentages is this.
Crystal.
No? Yeah, it is a crystal. Good. Calcite is calcium carbonate. That particular crystal is the middle form, or the crystal form of the middle form that's in shell material. And so each of these little shell fragments that you see is made up of a calcium carbonate compound. These are the most common constituents in our shoreline sediments. We've got quartz, feldspar, biotite, which is a mica, calcium carbonate, garnet, and a few residual minerals like ilmenite and magnetite, which are also iron minerals, heavy minerals. Now, what's important about these are the way they travel in the near shore. And when you think about how they travel, you think a little bit about what their characteristics are of the medium, the stuff that actually moves this sand. Now, what is moving the sand is a fluid. And a fluid is something, of course, that deforms continuously under stress. It can be water, it can be air, it can be the inner core of the earth. minerals, molten minerals. Any of these things are defined as a fluid. So fluid has certain characteristics that allows it to pick up and entrain these particles into the water column and move them under certain conditions. Now, you just push your hand down on the sand and rub it a little bit. You'll feel movement. You'll feel the sand grains rolling under your hand. One of the things that helps to entrain particles is the effects of pressure. And that's what happens when you have large volumes of fluid over top of sediment. The other thing, of course, is the velocity of the fluid that moves it. Now, I almost hesitate to tell you this, but gently, not in each other's eyes, if you blow very gently across the surface, very gently, you will notice that the small particles start to move. They'll start to roll. They'll be entrained into that fluid column. Remember, air is a fluid. Now, if you blow a little bit harder, you'll see that the larger particles start to move. And if you blow very hard, the very large particles will move. Now, this is a characteristic that's very important when you're talking about the capacity, the capability of water to move sediment in the nearshore region. And it's something that's very difficult to study because you're taking measurements in an area that has a lot of turbulence, that changes rapidly, one that's not really conducive to sitting there and taking measurements. Consequently, we have to develop a number of techniques to allow us to do that. Now, of course, the other thing that we need to be concerned about when we're talking about sand on a beach is we're talking about a resource. This is something that has value. It's something that provides certain other cascading values. And most of you probably participated in Earth Week last spring, and you tend to think of resources as living things. Wetlands, for instance, they provide habitat for fish, fish nurseries, and certain other important functions like water quality filtration. Sea mammals you tend to think of as a resource. We have endangered species that we're concerned about because they are valuable resources. Our fisheries are considered resources. Our fisheries being in Virginia, the oyster industry, the clam industry, the finfish industry like bluefish and striped bass. They're all resources. Sand is also a resource, but there's something very different about it. Where if you catch fish and you overfish a particular species, you can leave it alone for a few years. It'll start to reestablish itself. Reproductive strategies will take over and you'll start to replenish that resource. Sand isn't quite so easy to replenish. How many of you still have your sand in your hand? How many of you dropped it on the floor? Well, what you just dropped on the floor in the space of, 7 or 8 minutes took nature approximately 200 million years to form. Now, when you think of what you have done in terms of resource loss, we're talking about a non-renewable resource. You have callously thrown away something that has taken a major portion of the last 2 geologic eras to form. Something that you might want to think about the next time you throw out a truckload of sand somewhere. But this is not a resource that is easily renewable. Well, let's talk a little bit. I'm guilty of the same thing. Gone. Well, let's look a little bit at why we're studying this. Some of the concerns that people have over loss of sand. You know, where the little infrared thing is on the head. Okay. We've all seen this sort of thing, or at least any Nighthawk, and I'm sure lots of you have gone down to swim or to surf in Mag's Head. Perhaps next time when you're surfing, consider yourself as a particle on that water surface, and consider what the forces are as you approach the shore. More. And of course the aftermath. Again, like I said, there's a considerable amount of force vested in waves. And wave energy itself translates onto the beach. Now, the purpose of a beach in a natural system is to absorb that wave energy. It protects the uplands. It allows energy to dissipate through frictional contact with the beach face. Now, in a natural system, that's wonderful. You want to have waves attacking a barrier beach. You want to have a lot of overwash. You want to have that beach maintain itself through the transport of sediment along the beach and across the beach. When we start having problems is when people start building things on the beach. Because suddenly you've got a barrier there. Water can't go across the beach. Sand can't go across the beach. And of course, whoever's living there has got a considerable amount of money invested in that structure. And he's more than a little bit concerned about getting his feet wet. Now, what we'll talk a little bit about today is Mr. Erosion. Erosion itself is not a concept that's easily translated into scientific study. There are a lot of rules of thumb. Well, if we just put out a structure, if we build a big rock wall, if we put out a lot of drawings, then that will stop the flow of sediment, that will protect us from the waves, and everything will be all right. Well, as I said, working in the surf zone is a very complex project. There are a lot of different forces, and there are a lot of different things that contribute to erosion. And these different elements contribute in different amounts in different places. There's a strong regional aspect to an eroding shoreline. We see the evidence of this in things like houses falling in. We see the evidence of this in things like heat outcropping on the shoreline. Now, you all are familiar with heat. It's an organic material that comes from compression, successive compression through many years of decayed organic material. And what we're looking at here is what was once this backside, the marsh side of the island. It used to be here. The beach would have been out here somewhere. Through time, sand has been picked up during storm activity and moved across the beach, allowing the beach to roll over, allowing the beach to absorb the energy, but to maintain itself. And what we're seeing now is the beach moving back across what used to be that barrier section. Other evidence of that, in this particular case, this is what was a beach area. In Louisiana, those are mangroves that were on the backside of an island, are now in the surf. And even more to the point, this is again in North Carolina, these are cypress stumps. These are the remnants of a large forest that existed along that area approximately 4,000 years ago. Now, the island in that area is about a mile wide. So you're looking at a total translation, a movement of the island of approximately 1 mile in the past 4,000 years. Well, that doesn't sound like a whole lot, but there are other factors besides just natural cross-shore movement that affect the rate at which sand disappears from a shoreline. We've mapped a lot of shorelines in historical time, and we've been able to see that a shoreline will recede at rates that can be as much as 100 feet, 200 feet per year. The north end of Cedar Island, which is one of the Virginia Barrier Islands, has been documented through the past 20 years at receding at rates greater than 75 feet per year. That means that if you build a house right here, Next year, and the water were back at the back end of the auditorium. By next year, this house will be gone. We've had 1 year of effective life in the house. You see a large amount of movement of the shoreline. Okay, here we go. Well, what are the reasons for this movement? Well, there are a number of reasons. One of them is a global perspective, and that's sea level rise. Now, I'm sure you all have been hearing in the newspapers and in the classrooms about the problems with accelerating sea level rise due to changes in global temperatures, the greenhouse effect, the melting of the glaciers. Over the past 10,000 years or so, we've been seeing a constant rise in sea level. This is associated with the decline of the last glacial age, which reached its peak about 18,000 years ago. From about 12,000 years ago till now, we've been seeing the sea levels rise. And over the past century or so, they've been rising at something in the neighborhood of 1/10 of an inch or so per year. Not very much. But if you talk about a large number of years of this, the incremental effect is quite extensive. Now, this is a good point to illustrate another concept about the changes in shorelines. There's a big difference between talking about shoreline recession and shoreline erosion. It's a very critical difference, and it's something that any astute consumer of the shoreline, be it in a recreational sense or buying houses, ought to be aware of. Now, let's assume all you folks are water down here. Up until, say, this row. All you guys are sand. Each one of you are sand particles. Now, if you all turn around in this row, this is now today's water level. And look behind you. What level? What do you see if you look directly behind you? You probably see these people's necks or chins. You're at about this level. Water level is now here. Okay, stand up, each of you. Okay, now turn around. Now tell me, where do you see if you look straight out? What level do you see? Right. About here. You folks are all underwater now. Sorry to tell you. We've had a sea level rise of, maybe 2 or 3 feet. You folks are still fine. You're on the beach. You're okay. Everybody from here down is now inundated. The shoreline has moved from that row to this row. But all these grains of sand are still here. They haven't moved anywhere. The shoreline has receded, but it's a matter of inundation, a matter of flooding. Water levels have come up. All of the material that was here before is still here. That is a shoreline recession problem. That's the kind of problem any of you guys who've been up to West Point or who live up in that area, you'll see there's some very rapid subsidence of the shorelines along the Pamunkey and Mattaponi. And the subsidence of those shorelines is resulting in increased water levels. Now, let's say these folks down here, all this water gets real agitated. We've got a storm. It's rolling it around. It's got waves, and it starts to grab at the sand on the beach. It starts to grab at you folks and move you out. Suddenly you're not sitting here anymore. You're sitting way down there. Because the water has carried you further offshore. You've been eroded. You are no longer part of the beach face. You have been picked up, entrained, and moved somewhere else. Those are the two critical portions of erosion, is entrainment and transport. Now, in many cases, and one of the reasons why storm damage is so extensive is because the wave forces associated with storms are large enough to transport particles out of the immediate shore face area. And therefore, that sand, sediment, is effectively lost to the system. It has been eroded. And an eroded shoreline is a much different problem to deal with in a management sense than a receding shoreline. Okay, very important in a global sense, in a large-term sense, about the health of your shoreline is your sediment supply. How much sand is actually available to be moved? If you have a very thick sand deposit, you can withstand a lot of movement of sand along the coast or across the coast. The amount of sediment supply coming in will be sufficient to withstand or to overtop whatever the inundation is due to sea level rise or whatever the changes are due to changes in wave energy. If, however, you have an area that's sand-starved, you're going to have to tell me. I can't tell from the sand. An area that's sand-starved, in this case there's very little sediment available and no sediment coming in, the impacts become a lot greater. And you can see, suddenly it doesn't much matter whether you have a lot of wave energy, very little wave energy, a lot of sea level rise, or no sea level rise. There's no sediment available to the system. Consequently, you will not see a beach. You will be seeing increasing shoreline recession, increasing changes to the bacteria habitat that have nothing whatsoever to do, well, that's not true, but less to do with the processes and more to do with the sediment supply. So that's something else that's really important. Now, the things that are something that can be dealt with are those aspects of shoreline change that are related specifically to the characteristics of waves and currents on the beach in the surf zone. This little schematic is a couple of terms. Most of our beaches, open ocean beaches, and some of our bayside beaches follow a general configuration of an inner bar and an outer bar. This allows for a lot of dissipation of wave energy during storms. Storms will tend to break along the outer bar and dissipate energy because of friction along the bottom. Water is moving along the bottom. The friction of the water as it moves allows it to dissipate energy into the sediments at the bottom. It'll be moving some of those sediments both onshore and offshore. And you will see a significant change in that configuration. Now, during fair weather conditions, when you don't have quite as much wave activity, the profile tends to straighten out. You don't seem to have quite as many bars. But you can see how material becomes entrained by water particle motion as it touches the bottom. And during fair weather conditions, it tends to push that material back up on shore. Consequently, you'll see a rebuilding during fair weather conditions of material that was moved offshore during storm conditions. It's part of the natural balance in the system. Okay. All right, well now, what actually happens to material once it's up into the water column? Where does it go? How do you get rid of it in an eroding system? Well, if you look at any particular shore face compartment, there are a number of different places it can go. One thing that it can do is it can move along the shore. Waves that approach a shoreline at an angle will tend to create, as a result, a longshore current. That current, and I know you've probably all felt it at various times as you stand in a surf zone and you feel the water moving past you, not in the bay shorelines where you're looking at tidal forces, but on open ocean coastlines. That's a longshore current generated by the incoming wave characteristics. The other thing, of course, that you will feel oftentimes is on offshore transport due to shore normal currents. These are like brook currents, what we term a cellular circulation. Water comes in, moves along the coast, and then moves out in a rush. And if you've all been at the beach and seen the signs that no swimming because of brook currents, there's a strong component of offshore transport of sand and sediment in those types of situations. There's also a lot of offshore transport associated with storm waves. movement of sand from the shoreline is what we call overwash transport, where waves during storms pick up sand from the front of the beach face, move it across the shoreline, and transport through inlets. Now, you cannot underestimate the amount of sand that can be moved through an inlet. One of the reasons for this is because, and you'll see this in many places along the bay, because of tidal currents. Tidal flow into an inlet, as many of you know, or perhaps you know, you've probably done these experiments in science class, to look at Bernoulli effects, the changes of velocity, how fast a particle moves as it goes through a constriction. And that is a constricted channel. So you have particles that are moving, water particles, and the sand that they're carrying along with them, moving slowly towards the inlet out here. They speed up as they approach the inlet, and they entrain more material. And as that material is entrained into the water column, it's pushed forward through the inlet on the flood tide, and then water spreads out. There's a much larger space. The velocity changes. Water slows down. It no longer has this capacity to carry the particles. And if you remember when you were blowing sand around, you couldn't move as much with a gentle blow as you could with a real strong one. Same, as your velocity slows, the sand particles drop out. And you create very large delta features. You can see those on the inside of this particular inlet. Now, once that material is inside, it begins to build up those shoal areas. Now, that's important. It's important for habitat. It's important for wetlands. It's important in providing a reservoir of sands. However, this is all material that has been coming off the face of the shoreline. So although the sand itself has not completely disappeared, it is the result of this type of transport is an apparent, a real change in shoreline position and an apparent loss of sand. For the person who built his house on the beach, he doesn't much care that the sand all stored back behind the sound now. He cares about is what shoreline is receiving. You talk about cross-shore transport. You also have to consider the wind effects, ale and there we go. Now, how many of you all have been hang gliding on Jockey's Ridge? There you go. You probably have felt this. This is Jockey's Ridge without the hang gliders. One of the reasons that it is a good place for hang gliding is the continual updraft from the northeasterly winds. You can see the amount of sediment, the amount of sand that gets entrained into the air column by the same types of forces that entrain it into the water column. And it tends to move that sand back. And those of you who've been doing the hang gliding at Jockey's Ridge for a long time know how much that dune has changed, how much it has migrated to the southwest, where it's starting to overrun some of the housing and forests of the developments back on the back side. An enormous amount of sand moves across an island by this process. Of course, the other element of this is moving sand across the island with water. Storm conditions. You see larger waves, more runoff. More water crosses the beach. It's carrying material. As it moves across the beach, it slows down and deposits it on the back shore sections. Remember the first slide that I showed you? That deposit was a result of an overwash event in a Lincoln's birthday storm in 1973. There was sufficient water moving across the island and carrying enough sediment to leave a deposit 6 feet tall across the width of the island, 6 feet thick. Covered the road, covered cars, a lot of this is a slide of post-storm overwash. You can see that it'll carry sediment all the way into the back part of the island. Now, where's this sand coming area moves across the island. Now, on a non-developed island, this is wonderful because you're maintaining island width and you're maintaining island elevation. You're just translating the feature. You're just moving the island over in space, but it remains a consistent feature. As long as there is no barrier, like a house, or any other thing to inhibit that flow across the island. That is indeed a very natural process and a very, very healthy one in terms of island mechanics. The problem, of course, turns up when you've got people who build along the beaches, and suddenly you've got a barrier to that cross-shore transport. And you can see the effects, the shadow effects. See the house in the middle here? See the shadow effect around it. Sand has moved as the water has moved around the house and been deposited in a shadow, a parabolic shape behind the house. You see this quite frequently, and if any of you get out to Cedar Island or one of the Virginia Barrier Islands, you see this very frequently, where you will have a barrier imposed and then the sand will move around that, drop behind it, but leave a shadow effect. Another reason why you lose beaches, this is sand bridge. I'm sure many of you have been down there. Most of you have probably heard about the problems that sand bridge is having with its eroding beaches and the bulkhead. This is sand bridge in January of 1987, following the storm. Now, the reason why sand bridge is losing sand is very different than any of the other cases. It's not a matter of having material moved from the shore face and moved behind it. There are too many houses to allow that cross-shore transport. It's not a case of a lack of sediment supply. You see stable shoreline, for instance, at Falls Cape, and the sediment source is the same down at Falls Cape as it is in Sand Bridge. You don't see any difference in sea levels between, say, Sand Bridge and the Virginia Beach Resort Strip and Falls Cape. So there's another reason that governs the pervasive erosion problem down here. And we'll see in a minute. There it is. Actually, if we can pull that slide down a little bit, it would help. The reason down a little too far. Well, we'll continue. Imagine this, if you will. The amount of wave energy that reaches the beach is a function of a number of different things. One of those is water depth. And as if you have deeper water nearer to shore, that will allow larger waves to reach the shoreline. More wave energy is directed expressly on the beach. Now, in areas like Virginia Beach, there's a real broad platform. There's a sand platform. There's very shallow water that extends from the beach face itself, the beach that you sit on, to about 1.5 miles offshore. Apparently, I've done terrible things. Slide better. Sand Bridge, however, has got a different situation. There's a very steep short Thank you. Well, you can see at the top where it says Virginia Beach. You can see the drop-off to that very broad platform. You can see the agitation. Wait a minute. You see the beach changing before your very eyes. Down here at Sand Bridge, is that? There we go. At Sand Bridge, you don't see that platform. You've got very deep water, very close to shore. Okay. Now, what are the impacts of this? There are two impacts that are really controlling a very long-term and very severe problem here. One is that the very deep water, very near the shore, allows, during storms, larger waves to actually break on the shore face than break on the shore at Virginia Beach, several miles to the north. Consequently, you've got more energy directed on the beach face that is in training, picking up the sand. The other problem that we've got is that once the storm waves start to move the sand a little bit offshore, it ends up in very deep water, and the force of gravity takes over. These storm deposits end up a considerable distance offshore. And for that matter, in some of the surveys that we've done when we've been taking cores offshore, we find beach face sands spread in a thin smear over the inner shelf at water depths somewhere in the neighborhood of 35 to 40 feet, and at distances 1.5 to 2 miles offshore. Now, the problem with this, of course, is that you're in fair weather conditions when you've got when you don't have storm waves, you have swell waves that normally will push that material ever so slightly, ever so slowly, back towards the shore face. They can't reach that deep. Those waves aren't large enough, so you don't have water particle motion at those depths. And so the sand just stays out there. Consequently, this is a very, very good example of a truly eroding beach. Material is picked up, material is moved out of the system. It's gone. Consequently, there's actually very little you can do in a structural sense to try and protect this beach. It has a very severe problem that is dictated by the geometries of the offshore. Storm waves. Something that we've all seen and all been concerned with. Energies associated with storm waves are very different than the types of forces associated with fair weather waves. Storm waves tend to be short waves, very steep waves, very choppy waves. There's a lot of turbulence associated with those waves, and consequently a lot more per wave. A lot more sediment is entrained and moved. In this particular case, you can see the sediment laden waters as it's created in the escarpment. In this case, again, I should remind you, our problems in Virginia are not isolated to the open ocean. I should point out that this is directly offshore VIMS in the New York River. And you can see the bands of sediment, that tinted water, tan water, moving along the coast. And this particular one is a 1985 storm. Now, how do we know all this? How can we go out and measure? How do we know enough about the shore waves to be able to do something about it, to be able to help? Well, one of the things is a series of instrumentation. This particular tripod is outfitted to measure waves and currents. This is a pressure gauge. It measures the pressure of water moving over it, which allows us to know something about its depth, something about the sea surface, and consequently something about what type of waves we have. The other way, of course, is stand out in the water and you measure. These folks are taking beach profiles. They're looking at changes in the slope of the beach and how the bars and troughs move through time. And so there's one step. On the top of that is mounted a series of prisms. And those prisms are there's an instrument that sends a laser beam to those prisms, which is reflected back. And the distance and elevation can then be calculated. Now, you probably don't mind being the person holding that rod in these type of conditions. But there we go. In these sorts of conditions, you probably would be less enthused when your project manager told you to go just a step further. Just step back another 5 feet and we'll be done with this survey. Well, that was a good measurement. Step back another 10 feet and we'll try it again. Needless to say, you'd be less than enthused about your job in those conditions. So what do? Well, we need to build instrumentation that will allow us to measure offshore. This is a CRAB. CRAB stands for Coastal Research Amphibious Fund. The CRAB happens to live at the U.S. Army Corps of Engineers research pier in North Carolina. And it is designed specifically to measure offshore configurations, the actual elevation of the seabed during highway conditions and moving fairly far offshore. The crab is 35 feet tall, and these are these wheels. Perhaps you can see there's somebody standing right there, so you get an idea of how tall or how large the wheels are. The wheels are filled with water, so they're neutrally buoyant. Consequently, they don't sink into the sand. They travel across it. And it's powered by a Volkswagen motor on top. Now, you never thought a little bug could do quite so much. But this has really revolutionized the development of this equipment. It's revolutionized our ability to survey and to tell what's happening during storm conditions. And what I want to do now is run a real short video for you that shows changes in bar systems and how the sand is moved offshore and onshore through time as measured by that particular instrument. Or maybe we won't. Okay? I'm not sure what the grid is, but it's something that seems to be generating itself here. It's running on. It's running. Well, we won't see what happens then. If we get this work host during the wintertime, when we have a lot of easter storms that move a lot of sediment around, that the shoreline will recede for a period of time, but that sediment hasn't really gone out of the system. It's living, residing here in the very near shore. And during the summertime, that material moves back on shore, and the shoreline itself moves out again. And the shoreline mobility is a fact that's very important to know anytime you want to embark on any sort of a management decision relating to a shoreline. And that can either be management in terms of policy, whether or not you allow people to build on the shoreline, or whether it's in terms of engineering. Do you actually put the house there, and where do you site your house? Now, with all of that in mind, what do we actually do to protect our shorelines? How can we take care of this problem? Well, there are a number of things that we can do to mitigate the erosion problem. But you have to remember that anything that we put on the beach, anything that we put in the shore zone, does not change the fundamental processes that are causing the shoreline to recede. None of the structures that our present state of technology has allows us to stop sea level rise. None of our structures allow us to make storms go somewhere else. None of our structures will make the storms disappear. All we're trying to do when we put a structure on a beach is to either stop the movement of sand in the near shore, or to put somehow a barrier between the wave action and the structures that you've constructed. And then you have to keep in mind that if you put that barrier there, you're changing the dynamics. You're stopping what is supposed to be a very natural process. You're supposed to be seeing that movement of the shoreline back and forth. One of the most common and now lessons, you see a lot of them, are groins. A groin is a structure that is perpendicular to the shore, and it's supposed to stop sediment that's moving along the shore. And you can see how it tracks. You can always tell on a groin which way sediment's moving. It's moving in this direction. Because you can see that it's pounded, it's actually held up by this wall that's been built. Of course, there are other age-old strategies. Build a wall. If indeed you build a wall that stops one level of wave energy but not another, well, build another wall. If that doesn't work, build a third one on top of it until you get to the point where you actually have protected the structure behind it. The problem with this, of course, is that if you're going to build a wall, you're going to necessarily lose the beach in front of it. You're going to have to sacrifice that beach. Now why? Why is that a necessary trade-off? Well, one of the reasons why is that in areas where water levels are rising, that there's nowhere to create another beach slope by allowing the sand to move back across the beach. You stop it. The second reason is that when you have a very hard structure like this and a wave breaks on it, instead of dissipating wave energy gently over a slope, you're directing that energy either down or to the side. And if you direct it down, it is going to be picking up more sand. You're putting a direct force downwards that picks up that sand and gets it into the water column. So now you've created a structure that is compounded, making that directed force larger rather than dissipating. Consequently, you can create some very severe scour problems as well. Another way to deal with it. Is that better? Is breakwater. Now, breakwater is designed to be out in the water. It's designed to do exactly what it says. You put it out in the water, and you allow waves to break on it. So you're dissipating the wave energy offshore rather than on the beach. That creates an area of quiet water behind it where sand can be deposited. There's actually, these structures have been used very successfully in the Chesapeake Bay. And if any of you have a chance to travel, either recently or in the near future, across the Hampton Roads Bay Bridge Tunnel, take a look at Willoughby as you drive by. You'll notice they've just finished a project there, where they have built two breakwaters like this, and you can see this spit. Now, this spit of land that goes out is called a tombolo, and you can see that tombolo starting to form behind both of these structures as sand is deposited in the lead, in the quiet water behind those structures. Another very popular alternative now is what we call I can spend most of the evening explaining this. This is what we call a soft structural alternative. We're not putting rocks, we're not putting wood, we're not putting sheet pile, we're not putting steel. Nothing hard. This is sand that's being pumped back onto a beach. Think of it as recycling. Sand moves from the beach offshore, sand will move into an inlet, sand will move across shore. You take the sand from wherever it's been moved and you put it back on the beach. It doesn't stop the processes, it doesn't stop the erosion, but it allows you to maintain a beach width through time in what is a more environmentally sensitive way. Because you haven't changed any of the environmental constraints either. You're putting the same material back. Consequently, the organisms that inhabit the bottom areas can recolonize and continue to live in that area. The natural processes that are taking place continue to continue. How many of you were on Buckrow Beach this summer? Did you watch the beach fill operation going on there? In that particular case, the city of Hampton mined sand. They actually dug a pit about 2 miles offshore and brought that material on shore along with a few shells of various varieties. And as they say, you can get a bang on Hampton beaches this year. But what they have done is follow this alternative, soft structural alternative. They expect the sand to move again. And they are expecting to have to pump more sand on in probably about 7 to 10 years. But it allows for this beach width to be maintained for a period of time in a more environmentally sensitive manner. Now, last, as we discussed, the sand that's on our beaches and in front of our houses and that we use for both recreational purposes and use protection for those structures is effectively a non-renewable resource. We are not generating sand in volumes these days that are replenishing our beaches. And we've got millions of years to wait before we can really generate large amounts of sand. And one of the reasons for that is development upstream. We're not allowing the natural processes to erode the mountains, erode the foothills, and bring that material slowly down. But beyond that, we also have to consider that there are a number of forces, wave and wind forces, that actively entrain that sediment, actually pull that sediment up from the bottom and move it somewhere. And so we've got a continuing problem. Those processes are processes that are not going to change by anything that we do. There are ways to mitigate those processes, but we can't stop them. The other thing that we've got to keep in mind, though, is how much is too much. When do we make the solutions so great that we, in this particular case, have obviated the reason we're actually living on the beach? And that's something that we all have to give some careful consideration to, is when is the cure or the solution worse than the problem itself? As a final word, I'd like to let you all know that we at VIMS have been doing Virginia Institute of Marine Science. We're right across the York River, for those of you who haven't been down there. But we've been doing a lot of work recently in a number of different fields, not just erosion control, but we have a number of demonstration projects where we are actually studying how structures are affected. We also do a lot of work with organisms, oysters, wetlands, what the various interactions are. And we do indeed like to have visitors. We'd like to show you what we're doing. We welcome each and every one of you. We'd like to come over to see a little bit about the types of research that we do in the Bay. And we'd like to encourage you as well. We also have an active program where we have high school and college kids in and summer aid. So any of you who've got an interest in marine science, I think you might. I'd like to encourage you to perhaps consider working as a summer aid. If I answer any questions, I'd be glad to.